Application of vectors. Our first one here is we're going to talk about navigation problems. If you notice here, we have this airplane. And this airplane's course and ground speed is going to be projected at this V3. We have this drift angle between the ground, the plane's heading air speed versus the speed coming from the ground, okay? And then we have the wind direction speed going up against the plane. So let's read the application problem. It says forces of 12 pounds and 18 pounds act at an acute 90 degrees angle. Find the magnitude and the resistant force and the angle the resistant makes with the first force. So let's talk about it. Let me scroll up and make me some room here. So what we want to do is we want to draw. If you could ever draw and label, it makes it a lot easier to determine what part of the equation and what we're solving for. So what I'm going to do is I'm going to label for you, I'm going to label 12. And I'm going to let V equal 18, okay? And now let's look at it. We have two non-zero vectors that we called U and V. And that could be added geometrically to by placing it on the tail of these arrows. We can place them down here, right, whichever direction the arrows are going. So this one here, we can draw that way, and then this one that way, and then this one. So there we go. Now this longest side over here, I'm going to say U plus V, because whenever we talk about a triangle, the two short sides add up to give me the longest side. So I know that. I'm going to call this angle right here theta. This angle here is going to be what gives me my 90 degrees, because this is a right triangle. All right. Now that I know that, I can use the Pythagorean theorem, and I'm going to redraw just one more time, and I'm going to plug in. Or you could have left it that way, you know, what I want to do. Oh, let's leave it that way. Let's not do extra work. Let's label, let's call this U plus V, let's call it W. Or, you know, call it whatever you want, just make sure that you differentiate what is what. All right, so now I'm going to use the Pythagorean theorem. And when I use the Pythagorean theorem, we know that it is A squared plus B squared equals C squared. Well, in this case here, C is going to equal W. We're going to let A equal U and B equal V. So now I got W squared equals U squared plus V squared. And we're going to plug in what we know. Well, we know that U is 12 and V is 18. And we're going to square those two. And that gives me 122 plus 324. Add those up, 468. However, this gives me W squared, and I need to know what W is. So to undo the square, we're going to take the square root. Whenever you take the square root of both sides, you usually get a plus or minus because it's an even root. However, we're not looking for a negative length. So we're just going to look at the positive. So when I do that, now I get W is equal to 6 square root of 13. And let's round to the nearest tenths. It's approximately 21.6 pounds. All right, now that I got that, let's find the second angle, okay? So now when I look for the second angle, we know, okay, so what do we know? We know that adjacent and the opposite, we know those two things, right? And whenever we talk about that, then I know that I can use tangent of some angle. And we already know what theta is, it's 90 degrees. Let's do alpha. And we know that it's going to be sine over cosine, just a refresher, which is opposite over adjacent. Knowing this, I got 18 over 12. We can reduce this, or we'll just leave it in that format. What are we solving for? We're solving for alpha. So that means we need to take the inverse of tangent. Okay, now I'm going to plug it in my calculator, round to the nearest whole degree, and I get 56 degrees. And that is my two answers. I got my magnitude of the resistant force and I got my angles. Here's my magnitude of the resistant force and here's my angle of the resistance force. All right, let's move to our next one. Our next one says we have two prospectors. Here we go, right here and right here, that are pulling on ropes attached to the donkey's neck that does not want to move. The prospector pulls with a force of 50 pounds and the other prospector pulls of a force of 70 pounds. So here we go, we got those two right there. If the angle between the ropes is 30 degrees, as shown in the image below here, then how much force must the donkey use in order to stay put? The donkey knows the proper direction in which to apply the force. All right. So we're going to use a here, let me write it down. Parallelogram. Just in case I pronounced it incorrectly, we're going to use this. And we're going to finish drawing it out. So what do we got? We got these vectors. And I'm going to just draw this one coming out like this. And then we got the vectors going to the prospectors. And from here, I can go. And now I got my parallelogram. So we can call this one A and this one B. Well, then what does it tell me about the middle here? It tells me it's A plus B. Because we're going forward, so we know we're adding it. The parallelogram law states that one force acting along the diagonal of the parallelogram with the magnitude equal to the length of the diagonal has the same effect as the two forces that form the parallelogram. So let the force exerted by the top prospector 50 be a magnitude of vector A, and that's what I did. And let's let the force exerted by the bottom prospector for 70 pounds to be the magnitude of vector V. And I called it B. So we're going to call it vector B. Combined force of the prospector is the resistance A plus B. So we got that all labeled here. Now we're going to find the measure of the angle gamma. Note that the opposite sides of the parallelogram are parallel. Therefore, these two angles are supplementary. So I'm going to find gamma. So these two will be supplementary. Well, what do I know? I know whenever we talk about triangles, we get 180 degrees. So here we are given the 30 degrees between the two. And when I subtract that, I get 150 degrees. So this is going to give me my gamma. Okay. Now remove the extra parts of the drawing and substitute the forces. So what I'm going to do is just redraw it. Sometimes it's easier. I'm just going to draw what I need. So I know this is 150 degrees. If I drew it better, it actually had more of a slant. I accidentally drew more of a, do this right quick. I got more of a 90-degree going on there. There we go. Kind of better. So I'm going to call this 150 degrees. And then when we notice this is the 50 pounds and this is the 70 pounds force that's going on. So notice that the values of the two sides and included angle are SAS, right? The law of cosines can be used to solve the triangle in which two sides and an included angle are known. So let's use the law of cosines. And when I go use it, I notice that I get gamma. So I want to use the C squared equals A squared plus B squared minus 2AB cosine gamma. I know what A and B is, so we're just going to plug in everything we know. So B is going to be 50 squared plus B is 70, then we square it, minus 2 times that 50 times that 70 times cosine of 150 degrees. All right, so when I type this in my calculator, I'm going to go ahead and square the 50 and the 70 and add them together. And I went ahead and took cosine of 150 degrees. multiply that negative 7,000 to the negative square root of 3 halves. And now I get this. All right. Now let's add those two together. And I'm going to put approximately there because, you know, we have to round sometime. Just don't round too much right now. Now, that gives me c squared, and I need to know what c is. And I'm going to undo that square by taking the square root of both sides. I'm going to take the square root of both sides. Now I get c is equal to, approximately equal to 116. And that answers my question. The donkey must be, in order to stay, he must apply 116 pounds of force. All right. Let's move on to the next one. The next one says a block of ice weighing 70 pounds resists on a 40-degree incline. What force parallel to the incline is necessary in order to keep the ice from sliding down round to the nearest tenth, if possible? So what do we see here? We're going to draw this picture, and we notice that we have 70-pound block of ice on an incline of 40 degrees. We're going to draw the vector representing. So the R is perpendicular to the incline. So that force is against the ramp. And P is parallel to the incline. The vector G is representing the weight of the ice, the force of gravity. The magnitude of vector G is 70 pounds. There are two right triangles here in this picture. The original large triangle and the triangle formed by the vectors P, G, and R. Because G is perpendicular to AC and R is perpendicular to the incline, AB, the measure of the angle formed by the vectors G and R is the same as the measures of angle A, which is 40 degrees. The magnitude of G is 70. This is the hypotenuse side of the small triangle. The smallest angle in this triangle measures 40 degrees. So since we know this, okay, since we know that we have 40 degrees and we know that G is 70, we can go ahead and say I have sine of that angle is equal to my P over, because my P again is representing that is parallel to the incline, right? So we're solving for P. And G, we're going to divide it by G, which is 70. Now I want to solve for P, so that means I need to multiply both sides by this denominator to undo it. So now I got P is equal to 70 sine of 40 degrees. And I'm going to type it in my calculator and I get 45 pounds. And that is my answer. It needs 45 pounds force in order to keep it from sliding. All right, let's do number 4. We have this image here of a cannonball is placed in a 12-degree incline. And this force is 3.5 pounds is required to keep the ball in place. We're going to determine the weight of the ball. So we're going to draw the picture. This case, draw the rubber ball on the incline. So we've got one already here. In the diagram, the angle POT, we're going to call it 12 degrees. Let me clean this up right quick. Okay, so POT is going to equal the degree or the angle of 12 degrees. The vector PS is going to have the force of 3.5 pounds needed to keep the ball in place. PR is the force of the ball acting on the ramp. SPR is going to be the 90-degree angle. PQ is the weight of the ball. So let me just write that down. The weight of the ball. Let me go back. I skipped one. PR is going to be the force of the ball on the ramp. All right. And then PQ is greater than the magnitude of PR. So PQ is greater than the magnitude of PR due to the incline of the ramp. Okay. So we'll read on. Notice that the vector PR is the resistance of the vectors of PS and PQ. Therefore, you can draw a copy of the vector PQ that it begins at S and terminates at R, okay? So now refer to the triangle PSR. So I'm gonna PSR. So we got this triangle going on here. And since the measure of the angle POT, so we have the angle of POT is 12 degrees, the measure of PRS, so now we got the measure of PRS is also 12 degrees. Okay, so that helps out a lot. So since the measure of SPR is 90 degrees, we already have that up there, don't need to write that. Let me write down that one I just said to you. The PRS is going to be also 12 degrees because that one is 12 degrees. Okay, since the measure of the angle SPR is 90 degrees and the measure angle PRS is 12 degrees, you can use the law of sines. So let's use the law of sines. So what do I know? I got sine of PRS over the absolute value of PS is equal to sine of RPS. And I got my R in, let me see, it's PR. It's going to be SPR. I knew I did that, SPR, and absolute value of SR. Okay, so now let's plug in what we know. I'm gonna come over here. So sine of PRS is 12 degrees over, well, PS is 3.5, and that's equal to the sine of SPR, which is 90 degrees. We don't know what SR is. So now I'm going to undo, okay, so we're solving for SR, and if you notice SR is in the denominator. So what I'm gonna do, I'm gonna look at the fact that I have two fractions, two ratios equal. I got this equal sign separating two ratios, two fractions. Knowing that, then I can say, oh, okay, well, let's do this. Let's cross multiply. Let's take what's in the denominator and bring it up here. Let's take what's in the denominator and bring it up here. When I do that, this is what I get. I get the absolute value of SR times the sine of 12 degrees is equal to 3.5 sine of 90 degrees. Now I need SR, so what I can do here is I can divide by this 12, sine 12 degrees to both sides. Now when I do that, this reduces down and leaves me with the absolute value of SR and equal to 3.5 sine 90 degrees, all divided by sine of 12 degrees. I'm going to type this in my calculator. We can round this to the nearest tenths. 16.8 pounds is what I get here. So the weight of the ball is 16.8 pounds. All right. Okay, let's move on to the next example. A force of 23 pounds is required to hold a 73-pound crate on a hill. What angle does the hill make with the horizontal? And we're going to round to the nearest integer. So what I'm going to do is I'm going to go ahead and draw this out the best I can. So I got this hill. And then let's go ahead and get the rest of this drawn. So I got this crate, right? And it's going up this hill. And then it has this force. Okay. And I know from here to here is the force required to hold it. We're going to call it 23. I know that the crate, it says to hold the crate on the hill, we need 73 pounds. And we got this angle theta going on right here. So represent the force required to hold the crate on the hill as a vector parallel to the surface of the hill. We represented the weight of the crate as a vector downward direction. So let me draw this just a little bit. At 73, I really didn't give myself enough room to write it right here. I needed to write it here. I just didn't want it to get in the way of that 23. And this arm should finish coming down. So I'm going to just redraw that. So coming down from the crate on the hill, we got this 73 pounds. And then that is the weight of the crate as a vector, right? Because the crate weighs 73 pounds. And then it's going to go up. Well, what is that? That is the crate on the hill as a vector parallel to the surface. And that is the force, which is 23 pounds. So we got this going on. Okay. The angle of the inflation of the hill is the same as the theta. So the angle between the resistant and the 23-pound force, since angle theta is acute angle of the right triangle, use the right triangle trigonometry. The length of the side opposite of theta and the length of the hypotenuse of the triangle are known. Therefore, use the definition of sine to find the measure of the angle theta. And what we know about sine, we know sine theta is equal to opposite over hypotenuse. So what we're going to do is we're going to plug in what we know. So I got sine theta is equal to 23 over 73. And when I go to solve for theta, I need to take the inverse of sine. Type this in my calculator, round to the nearest whole degree, I get 18 degrees. So the angle that the hill makes with the horizontal is approximately 18 degrees. All right, so let's finish up.
But I'm gonna take that test.
The lockdown browser one?
Yes.
Is your computer working? Okay. I remember telling you come over just in case. You said something about taking it here, and I wondered if you was having trouble with it still.
Yeah.
Where did you want to take it? And did you want me to take you to a room where you can take it, or?
I will.
Okay, I'll take you into this room. If anybody says anything, say Miss Wilson. And I'll go tell Miss Gill. Is that the only one that you had to do? Is the lockdown browser or the midterm?
The midterm lockdown browser with the whole.
Okay, not the lockdown browser quiz.
Yeah, not the
That's what I was thinking. I thought, wait a minute. I got another student that's having trouble with the lockdown browser. So I knew you were coming and one other student. And I'm in the middle of making a video. All right. We're taking it right now. Just in case there's any trouble. And you haven't taken it at all, right?
I've taken it twice, but like it wouldn't go through, so I wasn't actually on the quiz, just like.
And if you have any trouble, you can come back in here. If my door's shut, it's just because I'm making a video, so don't knock, just crack it open and that way I can, or you can wave in the window and I'll pause it.
Okay.
So that's the only time I shut my door. It's when I'm doing the videos. Just because if not, I can get everybody talking.
Yeah.
Are you talking to me?
Yeah, I said, I thought about Dark, I let Darnell leave there because I heard them out here and never went back in there. But anyway. I hated it.
You see it?
I thought, oh, you put more.
Yes, it's for brought more information. I'm on board.
you looking for that? Yeah, right there. I don't know. Hey, where's the other? Hey, I'm not going to touch it on my computer.
So now let's do the next example. A plane has an airspeed of 131 kilometers per hour, and it's flying with the bearing of 79 degrees, while there is a 26 kilometer per hour wind out of the northeast bearing 25 or 225 degrees. What is the ground and speed in the bearing of the plane? Hello. Well, I marked her name off my list. I appreciate it. Okay, so if you notice, we have this this picture drawn right here, and we have that 131 with the angle of 79 degrees. We have the 26 with the angle of 225 degrees. Okay, now we want to know what is the ground speed and the bearing of the plane. Okay, so we got two things we're solving for right here. So let's do this. Something else we can do with this image, and I'm going to do my best to draw it neat on here on top of what we already got. So what I have here is this image here has, let's draw it. Draw the dotted line from here. I'm going to try. Let's try to make it straight. It gives me this angle here. And then we have this going on. And then we have from here to here. Okay. So now that I have all this, what I'm going to do is call this one V1, which is the 131. Okay. And then we're going to call this right here V2, which is the 26. Okay. So now that we have it, and now let's call this V3 right here. I put absolute values on it. All right. So the vector V3 represents the course of the airplane. So you need to find the magnitude and the bearing of V3. So what we're going to do is we're going to calculate the measure of ADC. And we're going to find that measure first. You notice that the measure of DAB, and if it will help, you may want to label each part. Let's just do that. I should have done that a while ago. There's A right here. Let's call this B, and let's call this C, and let's call this D. There we go. That'd be more helpful. All right. So now that I've done that, notice that DAB is equal to the 225 degrees minus that 79 degrees. When I do that, I get 146 degrees, okay? Now, since A, B, C, D is parallelogram, and the angles that measure DAB and measure ADC are supplementary, that is, the sum of the two angles is equal to 180 degrees. Well, knowing that, now I'm going to say, okay, ADC is equal to 180 degrees, and I'm going to subtract that 146 degrees we just found, gives me 34 degrees. Okay, now that you know the measure of, let me highlight this one. Now that we know this, oops, said I was going to. Let's highlight it right quick. Okay, now that we know this one, now let's move on. Okay, we are going to use the law of cosines to find the magnitude of velocity 3 or vector 3. So I'm going to take the absolute value of this. We're going to square it because we're using the law of cosines. We're going to set it equal to V1 squared plus V2 squared minus 2 times that V1 times that absolute value of V2 cosine of that measure of ADC. Now let's just plug in what we know. Well, we know what V1 is. It's 131. V2 is 26. Let's just finish plugging it in. And then we have cosine of 34 degrees. And then we're going to type that in our calculator. And we come out with 12189.59606. And of course, we got to take the square root of both sides because we want V3, not the square root of it. Or not it squared. Say that right. Okay, so now that I've done that, now we know what V3 is. V3 is approximately 110.4, and I rounded. So that's going to be kilometers per hour, rounded to the nearest tenths. Now, third, to find the bearing of the plane. So this answered the first question, right? This answered the ground speed. Now let's answer the second question. We're going to use the law of sines to solve for this one because we have sine measured DAC over the vector V2, sine measure ADC over V3, and we're going to plug in what we know. Well, we don't know what the sine of measure DAC, however, we do know what V2 is, it's 26. We know the sine or the measure of ADC, which is 34. And we know what V3 is, it's 110.4. And now what I'm going to do is I'm going to take this 26 and multiply across to this other side. Or another way to look at it is we have to undo the fraction. We're going to multiply both sides by the denominator to undo that fraction. I was hoping that would change. All right, so we're going to multiply both sides by the denominator. So what do I got? Now I got sine of measure DAC is equal to 26 sine 34 degrees over 110.4. Now we need this angle. So what I'm going to do is take the inverse of sine. There we go. And we're going to type this in the calculator and round to the nearest tenths. I get 7.6. Now we're almost done. Finally, we're going to add the measure of DAC to the original bearing. So the original bearing was 79 degrees. We're going to add the 7.6 degrees to it, and we get 86.6 degrees. Therefore, the plane's actual bearing is approximately 86.6 degrees. And let's get this. There we go. All right.